Hello and welcome to my channel. This is an educational channel that we focus on all kinds of different theories of everything, all-encompassing theories, cosmologies, paradigm shifters, holistic theories that can help you plug in with your own life and improve the world around you. And today is our 410th video on the reciprocal system of theory, which was originated by Dewey B. Larson back in the 20th century. And we're looking at one of his books called Basic Properties of Matter. We're in the first chapter called Solid Cohesion. Mr. Larson was a chemical engineer or mining engineer, one of the two or both. And he was working on a chemistry problem and having to do with the interatomic distance, and stumbled across some ideas that got him thinking about some things, worked out a lot of problems over the course of many years. And in 1959, he proposed his two fundamental postulates. It's basically condensing his work down to two sentences about how the universe operated. And then he took those fundamental postulates and he went through a process of deduction to determine his theoretical universe, what his universe would look like if his postulates were correct. And then in his books over the remaining years of his life up until his death in 1990, he compared his theoretical universe with the universe that the scientists had measured and recorded in their laboratories and their scientific tables. And that's kind of what he's doing here in this book, Basic Properties of Matter. He's looking at things like the interatomic distance, the compressibility, thermal expansion, melting point, critical point, boiling point, whatever you want to call it, and other basic properties of matter. And he goes through his theory and shows, provides equations for, like, okay, this is, excuse me, this is my equation for the interatomic distance. This is my equation for thermal expansion. And then he, goes through the whole periodic table, and he goes through many compounds as well, many molecules, and says, well, if plug in my equation, this is what my coefficient of thermal expansion would be. And for this element, and for this element, and for this element, and for this element. Now let's take my data and compare it with the data that has been measured by the chemist in the laboratory. And let's compare. So that's what he does in this book. And we're going to, we're going over the results. Now we're still in chapter 1 called Solid Cohesion. And he's laying the foundation. And laying the foundation is a seriously difficult task, because it's the hardest part about the reciprocal system is that you have to unlearn a whole lot of stuff before you can really learn anything. And he has to kind of carry you through that. And he doesn't necessarily always do that. He does that. Usually he'll do it. He does it very well with the kind of the literature review or the history of science review. So he will show you what their theory is and why it's not correct, and why it's going wrong. And he will use their own words to condemn their own theory. But then when he's presenting his theory, he sometimes takes a few shortcuts. Like, oh, I alluded to this in chapter 11 of my previous book. So if you're too lazy to go find his previous book and look in chapter 11 and read that, he kind of assumes that you've already read that because it's the first volume of his trilogy, and this is the second volume of his trilogy. We did read it, as a matter of fact, and those are videos that I did about 6 months ago. So you can go back and refer to his previous book is called Nothing But Motion. So if you go back in my archives, you can see that I went over the book Nothing But Motion in about probably 80, 90 videos. I don't know, a lot of videos. But for people who are just tuning in, you know, it's a little difficult to go back and figure out what he was talking about. So I'm trying to carry you through that, but there's a lot of kind of stuff like that where he's referring to things that he covered other places. And that's the difficulty with Larson, is that there's so much difference between the way he's doing it and the way that you're used to it being done, that it's difficult for him to carry the narrative forward at the same time that he carries all of the accessories forward. And he does have a lot of accessories, but what's interesting is that those accessories are consistent. So if you read his book on basic properties of matter, on chemistry, he uses the same accessories as what he uses when you read his book Universe of Motion, which is on astronomy. And he'll use even the same accessories when he's writing about economics in his book, The Road to Permanent Prosperity, which we'll be getting to eventually here as well. So he's not just making these things up, but it appears as if he does if you are just taking the books on an island and you're just taking them one at a time. You have to kind of see the whole picture. You have to kind of read all of the books before you realize that he's actually being consistent and not just pulling things out just because they work for him in this particular instance. So you kind of maybe just need to trust me on that a little bit. But Larson is being consistent, like where he's using the interatomic distance, or where he's figuring out the rotational forces. So we're going to backtrack just a paragraph when going through this, but we're going to move forward here, even albeit slowly, and trudge our way through these first couple chapters until we can get some kind of more solid foundation. Now, the basic idea behind Larson's theory, again, is articulated in his two fundamental postulates, and really in his first postulate, which says that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, summarized by me, I would say the universe is not made out of matter. The universe is not made out of energy or anything else, force or anything like that. The universe is made out of motion. And motion is the relationship between space and time. This sets up a generalized reciprocal relationship between space and time. And motion is basically a fraction, with space or time as the numerator and time or space as the denominator. Time and space can both come in multiple dimensions, 1, 2, 3, even 4, 5, and 6 dimensions. And all of our scientific quantities are relationships between space and time, such as speed. Speed is space over time. Energy is time over space. Acceleration is space over time to the second power. Force is time over space to the second power. Matter is time to the third power over space to the third power. And so on and so forth. And those can be derived in various ways, but they also are a valuable check on our work, because now he has boiled it down to 2 variables, time and space, as opposed to 3, from the MKS system, which is matter, meters, kilograms, and seconds. So time and space and matter. But for Larson, matter is just time to the third power over space to the third power. So that gets rid of matter. And now we're just dealing with time and space. And so that makes it much less cumbersome. Larson, when he refers to the universe of motion, he's referring to a specific kind of motion that is actually a more generalized and non-localized kind of motion that he calls scalar motion, which has been recognized by science but not recognized for its significance. It's kind of just a sideshow for legacy science. But for Larson, scalar motion is the fundamental thing that he builds upon. And a scalar motion is a motion that has a magnitude, but it has no specific direction. And the way to envision scalar motion is by a balloon with dots on it. If you blow up the balloon, all of the dots will be moving away from each other. But they're not moving in any specific direction, or rather they're moving in all directions. Each dot is moving away from each other dot. But there's no specific direction. That's basically like a two-dimensional scalar motion. You would fill in that third dimension if you use something like raisin bread. And if you put the bread in the oven and it starts to rise, all of the raisins will be moving away from all of the other raisins. That's also a scalar motion. Each one is moving away from each other one, but they're not moving in any particular direction. The only way that you get a particular direction is if you pick one of the raisins and say this one is motionless, or one of the dots on the balloon, and you say this one is motionless, and I will measure from all the other dots from this one, and that will give you the directions. But that is not a product of the motion itself. It is a product of the reference system. So it's the reference system that is giving you the directions, not the motion itself, which is scalar. And the same, and it can be applied also with an inward movement of that balloon. So if you suck in the balloon and all of the dots will be moving toward each other, it will appear as if the dots are moving due to a force of attraction. Like this dot is moving toward this dot, and so there must be a force field there. Otherwise, that's action at a distance, and there has to be a force that is explaining why this dot is moving toward this other dot. But that's not the case. It's just that all of the dots are moving toward all of the other dots, including these two that you're focusing on. It appears as if there is an attraction there, but there isn't. And the data, the measurements that you make it appear as if there is a force between them as well. It acts as if it were a force, but it is not a force. That's what Larson calls an as-if force. It's not a force, but you call it a force because it complies with all of the math of a force, but it is really an as-if force. It is a scalar motion that you have assigned a reference point to. Okay, now the other major thing is that space and time and motion come in only discrete units. You have to have a full unit of space and you have to have a full unit of time in order to have those things. If you don't have a full unit, then you don't have them. So, and the units are small, but not infinitesimal, or close to infinitesimal actually, but very small, but they exist. So the unit of space is 4.56 times 10 to the minus 8 meters. And the unit of time is 1.52 times 10 to the minus 16 seconds. And so if you have exactly 1 unit of space in 1 unit of time, you have what Larson calls unit speed. 1 over 1 equals 1. And unit speed is the speed of light. So in the reciprocal system, this is the center of the universe. This is the null point or the neutral point, the 0 point, the origin. Larson calls it the progression of the natural reference system. If you have an empty universe with nothing at all in it, you still have a motion outward at the speed of light in all directions. That is the default motion of the universe, and that's what Larson calls the reference, the progression of the natural reference system. The stationary reference system is what the scientists use. They make their measurements from 0 speed. Larson makes his measurements from the speed of light outward in all directions. And that means that it's the midpoint, and that half of the universe is moving faster than the speed of light. Half is moving slower than the speed of light. The speed of light represents a boundary between those two regions that Larson refers to as the cosmic sector and the material sector, respectively. And then within each one of those sectors is a sub-region that is in the place where you do not have a full unit of space. Then you don't have space, and so you only have time. That's the material sector. In the material sector, you have 3 dimensions of space, which is what Larson calls coordinate space. 3 dimensions of space in a still frame, and you have clock time. That's a scalar motion of time. Time is always getting later and later and later and later. That's in the material sector. In the cosmic sector, you have 3 dimensions of time. 3 dimensions of time, or coordinate time, and you have clock space, meaning that space is always getting farther and farther and farther apart, just like on an expanding balloon. So basically, when you cross that unit speed boundary, you switch. They are reciprocals of one another. The cosmic and material sectors are reciprocals of one another. And you have to switch the roles of space and time. So in the material sector, you've got coordinate time and clock space. In the cosmic sector, you have coordinate space and clock time. And the same is true in the material sector, where you get with less than 1 unit of space. Then you don't have space. You only have time, because the contents of the universe are space and time. So it's got to be one or the other, or both. And in this case, it's not space, so it must be time. Larson refers to this as the time region. And this is a region of where atoms and molecules interact, because that is less than, they interact in less than 1 unit of space. And same is true in the cosmic sector, but in the reverse, that if you have 3 dimensions of time in a still frame, but you have a region of less than 1, where the interactions occur less than 1 unit of time, well, you don't have time anymore. You only have space, because you have to have a full unit of time before you have time. And so then you only have space. So Larson refers to that as the space region. And that is the region of cosmic atoms and cosmic molecule interactions. Cosmic atom is known by legacy scientists as an antimatter, or a meson. Okay, so that's kind of laying some of the groundwork. Now he lays down a few other things here, talking about the time region. But so when you're talking about solid cohesion, you're talking about a balancing of forces between this outward motion, outward scalar motion, the progression is what he calls it, and the inward scalar motion, which is what he calls gravitation. But when you cross that unit speed boundary and you move into the time region, you reverse the directions of those forces. So normally the progression is moving everything farther and farther and farther apart, and gravitation is moving the dots closer and closer and closer together. But when you move into the time region, it turns out that gravitation is moving everything farther and farther and farther apart, and the progression is moving everything closer and closer and closer together. And at a certain point, those two forces reach an equilibrium. And that equilibrium is known as the interatomic distance. And so each element has an interatomic distance, or maybe more than one of them, depending on the orientation of the atom, how it's oriented. An atom is a combination of rotations. In Larson's system, the universe of motion, everything is based on motion. So an atom is not a bunch of electrons and protons and neutrons. It is a bunch of motions. And each atom has their own motion profile on the periodic table. For example, oxygen. Oxygen is element number 8 in the periodic table, meaning that it has 8 protons and 8 electrons and approximately 8 neutrons, maybe more. And in Larson's system, an oxygen atom is 2 primary two-dimensional rotations, 2 secondary two-dimensional rotations, and 1 one-dimensional rotation, or 2 negative 2 rotational, one-dimensional rotational motions. It seems pretty complicated, but it basically is just notated as 2, 2, negative 2. And each atom has a signature, three-digit signature such as that. And you can figure out the atomic number from those, and you can figure out a whole lot of other stuff from those 3 numbers. So those are the rotational forces of the atom. Again, these are as-if forces. Okay, so we're going to start reading from here, and we'll see if this makes any sense. And I'm just backtracking by paragraph. In this chapter, we are dealing mainly with what we are calling rotational forces. These are, of course, the same as-if forces due to the scalar aspect of the atomic rotation that were called gravitational in some other contexts. The choice of language depending on whether it is the origin or the effect of the force that is being emphasized in the discussion. For a quantitative evaluation of the rotational forces, we may use the general force equation, providing that we replace that was an equation he derived in the book Nothing But Motion, the previous volume to this. Providing that we replace the usual terms of the equation with the appropriate time region terms. So now he's making a change of the equation to adapt to now using it in the time region, the region of less than 1 unit of space. As explained in introducing the concept of the time region back in volume 1, equivalent space. So equivalent space is time. Equivalent space is the spatial equivalent of time. Time and space are reciprocals of one another. So time equals 1 over space, and vice versa. Space equals 1 over time. And so equivalent space, 1 over t, replaces space in the time region, and velocity is therefore 1 over time squared, because velocity is space over time. So 1 over time equals 1 over time squared. Energy, which is normally time over space, energy, the one-dimensional equivalent of mass, which takes, because mass is time to the 3rd power over space to the 3rd power. Energy, the one-dimensional equivalent of mass, which takes the place of mass in the time region expression of the force equation, because the 3 rotations of the atom act separately rather than jointly in this region, is the reciprocal of this expression, or t to the 2nd power. time over space, but space is 1 over time. So time over 1 over time, which equals time to the second power. Acceleration is velocity divided by time. So that's 1 over time to the third power. The time region equivalent of the equation F equals ma, which is the general force equation from Newton or whoever, is F equals Ea, equals time to the second power times 1 over time to the third power, which equals 1 over t in each dimension. So that is the force, or the as-if force. At this point, we will need to take note of the nature of the increments of speed displacement in the time region. In the outside region, additions to the displacement proceed by units. First 1 unit, then another similar unit, yet another, and so on. The total up to any specific point being n units. There is no term with the value n. This value appears only as a total. So that's how you add up the increments of speed displacement. And speed displacement is basically, how is this differing from motion at the speed of light in all directions, the progression. That's what you measure from. So speed displacement is the distance from the progression to what you're measuring. So that's, unlike the legacy scientists who are measuring from 0, Larson is measuring from the progression of the natural reference system. And so that amount is not necessarily speed, it is speed displacement. The additions in the time region follow a different mathematical pattern because in this case only one of the components of motion progresses, the other remaining fixed at the unit value, or speed of light outward in all directions. Here the displacement is 1 over x, and the sequence is 1 over 1, 1 over 2, 1 over 3, all the way out to 1 over n. The quantity 1 over n is the final term, not the total. To obtain the total that corresponds to n in the outside region, it is necessary to integrate. So now we're getting into minor calculus. It is necessary to integrate the quantity 1 over x from x equals 1 to x equals n. The result is log of n, the natural logarithm of n. Many readers of the first edition have asked why this total should be an integral rather than a summation. I kind of question that Larson even had many readers who even got that far into it to even ask that question. But if so, he had many readers who asked him why this should be an integral rather than a summation. The answer is that we are dealing with a continuous quantity. As pointed out in the introductory chapters of the preceding volume, the motion of which the universe is constructed does not proceed in a succession of jumps. Even though it exists only in units, it is a continuous progression. A unit of this motion is a specific portion of this continuity. A series of units is a more extended segment of that continuity, and its magnitude is an integral. In dealing with the basic individual units of motion in the outside region, it is possible to use the summation process, but only because in this case the sum is the same as the integral. To get the total of the 1 over x series, we must integrate. I don't think I've ever understood that paragraph, and I probably need to read it over again. but I probably could use to brush up on my calculus as well. But he's saying even though it exists only in discrete units, it is a continuous progression. I think that's what I have trouble with. Even though it exists only in units, it is a continuous progression. Okay, so to evaluate the rotational force, we integrate the quantity 1 over 1 from unity, the physical datum, or zero level, to t. So the integration of 1 over t dt equals log of t times the integral of 1 over t dt equals log of t. Okay, so that is the equation that he's going to be using for figuring out, I think, the force here. So if the quantity t is below unity in any dimension, there is no effective outward force in that dimension. In any dimension, there is no effective outward force in that dimension, but the natural logarithm exceeds unity for all values of x above 2. And the atoms of all elements have a rotational displacement of 2, equivalent to t equals 3, or more in at least one dimension. Consequently, all atoms have effective rotational forces. So he has determined through that equation what the force of each atom is. You just take the log, and the natural log, and he'll be plugging that into the equation. But he has to derive a few other equations before he does that, and we'll get into that tomorrow. If anybody has any recommendations about the best way to teach this, I would be certainly open. I'm trying to be thorough and to cover what he's talking about. But I'm just one guy, and I don't understand this flawlessly either. I've read it over a number of times, but there's some sticking points, and I've tried to kind of do the background. I'm not a scientist. But I'm doing the best I can. So I'm just trying to present the information. You might be able to extract it better than I could. So we will move on to the next section here, and we'll do that tomorrow. So thanks for tuning in today, and have a great day.